All right, hi, so my name's Rob. Today I'm going to talk about program alignment for relational verification. This is joint work with my co-authors Prasita, Mukherjee, and Benjamin, Delaware. So when we talk about program verification, we're often looking at a single program execution and we want to prove something about it. So here's a program that computes twice the square of its input. And we might want to ask, does it actually do that for all possible inputs? And there are lots of different tools that we have that can help us answer this question, which is great. But not every question that we have deals with only one program execution. We might have some that deal with multiple program executions, maybe multiple programs. Here's an updated version of double square that's, I guess you could say, optimized. It needs half the amount of loops to get to its result. And we might want to ask, do these two programs do the same thing? So these sort of like industrial strength verification tools for relational verification, which is what we call this case, are a little bit harder to come by. Which is a shame because there are lots of interesting relational properties that we might care about. They come up in practical software development and verification all the time, and we would like ways to prove these properties. So even if there aren't these industrial strength tools, there are many approaches out there to doing relational verification. I'm going to sort of bucket them into two categories. The first one I'm going to call bespoke relational verification, where the idea is that you come up with some formalization, maybe it's a Hoare logic or maybe some language theoretic approach to representing the relational verification problem, and then you write tools that leverage that relational verification formalization, and those tools can rely on some powerful abstractions or mechanisms you came up with, which is great, but the problem is you have to write and maintain the tools, which in practice, many of us don't have the resources to put into, for example, Daphne or one of these larger tools. So the other approach I'm going to call a single program intermediate representation. The literature often calls this product programs. We found that this is a little bit of an overloaded term, and some things that fit in this first bucket are actually called product programs in the literature. So we call them intermediate representations, but product programs. So the idea here is that you have your multiple programs you're trying to prove something about. You combine them into a single program that maintains the semantics of running the two programs independently, and then you hand that single program off to single verification tooling. So the advantage here is that you can leverage these industrial strength verifiers sort of for free, but not really, because you have to produce combined programs that are useful to the verifiers. So what do I mean by useful? Well, let's go back to our example. We have these two programs we want to prove something about. I sort of have one with a green bar and one with an orange bar. And one thing we can do to come up with a single program that does the same thing as executing these independently is just sort of rename the variables and then put them one after the other. So I have the entire green program, then the entire orange program. And this is encoded for Daphne, so I can hand this off to Daphne and verify, which I can, but only if I give it this sort of complicated loop invariant. The loop invariant has to be very complete in terms of how it summarizes what the loop does, so that information sort of percolates down as we go on. So we can do a little bit better, so we don't have to have such a complicated invariant. We can sort of group subprograms that are similar together. So here's a version of this. You can see the green bars are intermixed with the orange bars, and crucially, I've merged the loop bodies together. So now I can have a loop invariant that reasons about what's happening sort of as the loop goes iteration by iteration, because the two loops were doing something similar. So I have this much simpler invariant now, which is great. Notice that I did have to duplicate a loop body to line up the iterations. Remember, one of these programs had a loop that iterated half as many times as the other. So to make this a sound, keep the semantics of the original program soundly, I have to sort of duplicate the loop body here. Okay, and this problem in general of putting subprograms into correspondence to make verification easier is called alignment, and it's tricky. You have to sometimes transform the programs by unrolling loops or duplicating loop bodies. If there are multiple loops in the programs, sometimes you have to figure out which loops correspond to which. And the existing approaches in this space of a solution here sort of rely on people to come up with those alignments. They're not really, there aren't automated approaches. So we asked, can we find these alignments automatically? And that's what this work is about. So we have an approach called KestRel for doing that. There are three main pieces here. The first is we have an algebra of alignments that tells us, helps us understand sound ways that we can realign the program and still keep the semantics of the original two programs. We use a data structure called egraphs to represent the space of possible rewrites using these rules for alignments. And then we do a data-driven search to, once we have this representation, to find the best alignment that's represented in this egraph. So I'll sort of briefly go over these three pieces. The first is this algebra of alignments. This is inspired by work from Antonopoulos et al. From Popple 2023. And what we're going to do is we're going to have this notation that uses brackets to indicate when two subprograms are related. So here I have two subprograms A and B, and I put them in this bracket notation to indicate that they're related. I can have things that are single on the left, single on the right. I can sequence these related programs together. And I have control flows that appear at the algebra level. So here's a relational while that relates to loop conditions with two loop bodies. And then I have a set of rewrite rules that tells me how I can rewrite terms in this algebra in ways that preserves the semantics of the original program. So I don't really have time to go into detail on what those rewrite rules are, but I'll sort of try to give you a picture of what it looks like to use them. So we start out with our two programs here. We put them into this algebraic term, which is just the entire program on both sides of a bracket. And then we can start using the rewrite rules to regroup things, compose them together, lift whiles into relational whiles and things like this. And at any given time, we can take this algebraic term and sort of reify it back into our source language and get an aligned program that has the same semantics as executing the two programs independently would have had. Okay, so once we have this algebra and we have this rewrites, we want to know what are all the possible ways we can rewrite something so that we can start searching over it. So we use egraphs for this purpose. Egraphs are graph data structures that are designed to represent equivalence classes on terms under sets of rewrite rules. So perfect, that's exactly what we want to do. Each node in an egraph has a sort of a set of symbols that you can sort of choose. One symbol that's in each node and sort of pick that as your symbol to put into your AST or whatever, and then go down the branches and sort of do it recursively. So I'll give you just a brief example of what this looks like with an algebra that's maybe more familiar than the rewrite algebra. This is just Boolean algebra. So here I have an expression and I have an egraph which represents it. This egraph, the dotted lines are the nodes, and then the solid lines are the choices inside of each node. And you can see I only have one choice in each node, so I can only extract one term out of this, which is the exact term that I have here. But if I apply a rewrite rule to this egraph, I get something that looks like this. It looks sort of similar, but note that now I have an E node here that has multiple choices. So I can either choose the not and then go down the branches, and I'll get back this original term that I have, or I can choose the and go down the branches, and I'll get this other term, not A and not B. And I can keep adding rewrite rules to the egraph, and the egraph relationships and choices will get bigger until at some point I'll hit some saturation where there aren't any more productive rewrite rules to add into the graph. And then my egraph is representing my space of possible rewrites. Okay, so we take our algebra of alignments. We use that in our egraphs to sort of saturate the egraph and figure out what all the possible alignments we could have are. And we sort of compactly represent that in an egraph. And now we need to figure out what is the best alignment that's hidden, that's somewhere in that egraph, right? So we do a data-driven search for this. So to extract a good alignment, we first have to figure out what is a good alignment. So the answer to this question is ultimately a good alignment is one that makes the backing single program verifier work. So it sort of depends on the backing verifier, but we can be sort of heuristic about this and say that there are certain things that make it easier to reason about. One of them is fusing related control flow structures. So in our example, remember fusing the while loops together made it easier to reason about. Also, making sure that when we have loops that we fuse together, that those loops, the iterations terminate at the same time. If they don't, you have to insert these runoff loops that run off the extra executions that didn't happen in the combined loop, which is hard to reason about for one of these single program verifiers. And note that these kinds of properties we care about, some of them are syntactic properties, some of them are semantic properties. So this sort of suggests that the analysis we need to do to figure out what a good alignment is will be some combination of syntactic and semantic analysis. So here's what we do. We start out with some baseline extraction from the egraph, which maximizes the number of fused control flow structures. And we use this as sort of a baseline. And then we can find sort of neighboring, close by alignments by sort of tweaking the choices we make in these e-nodes. So we can take one of our e-node choices and choose something different and get a closely related alignment. And then we can use MCMC to, like simulated annealing, for example, to sort of converge onto an ideal alignment. The cost function that we're going to optimize as we do that convergence will be a semantic cost function. It will be over the execution traces for these candidate alignments. And this is the way that we can judge whether or not we have a good semantic alignment. And the details here I don't have too much time to go into, but I will refer you to the papers for the detail of this MCMC process that we do here. At the end of the day, when we put it all together, we have something that looks like this. So above this dotted line are things that are happening in our source code language, like C is what we used. And then below the dotted line, we have things happening in the alignment algebra land. So we start out with our two source programs. We embed them into the alignment algebra, into some original unaligned term. We put that term into an e-graph, saturate it with the rewrite rules from our algebra. Then we go into this data-driven loop where we find nearby alignments, run the aligned programs to come up with execution traces, and converge onto some alignment that seems ideal. Then we take that alignment that we found, we reify it back into the source code language again to get some aligned single program that we can then hand off to single program tools. So we tried, we used Seahorn for some of our evaluation. We used Daphne and Dicon for invariant inference for some of our others. This is what we found. So we took a bunch of benchmarks from the literature. We compared sort of the naive concatenative alignment with just the syntactic extraction from KestRel, and then the full semantic pipeline from KestRel as well. We found that KestRel was able to align and verify all of our benchmarks within a minute, except for one that requires synthesizing a novel loop, a guard condition, and that's out of scope for what KestRel currently does. We also had a suite of benchmarks that we found that used abstract data structures. So these have operations that we can formalize the semantics of and give that to the backing verifiers. We found that KestRel was again able to align and verify all these programs within a minute, except for two. One of them was this another one of these cases where we had to synthesize a novel loop condition, which is out of scope. And another one, we computed the alignment, but then our backing invariant inference generator was unable to generate a good invariance for it. Okay, so we also sort of looked at what is dominating runtimes as we do this verification. So the takeaway here is that for the smaller examples, the runtime's dominated by loop invariant inference. But as we get to these more complicated examples that require more semantic analysis, the simulated annealing starts to take over the runtime. So that's KestRel. Just to summarize, we have lots of interesting relational program properties that we want to verify. One of our approaches for doing this is to construct these intermediate single program representations, but aligning them is hard. So we have an approach called KestRel, which uses e-graphs over an alignment algebra to find those alignments, and a data-driven search to find semantically desirable alignments. And we found that to be effective across a suite of benchmarks taken from the literature. The code is available on GitHub, and I'm happy to take questions. There you go.
Question, please.
Hi.
Hi.
Thanks for the presentation. My question is that can your algebra handling the programs contains some complex data structures?
So yeah, we have a suite of benchmarks that look at using abstract data types, which so we can do like lists and stacks and things like this. We have to axiomatize the operations on those data structures. So like we have to come up with axioms. What does it mean to have a stack and pop something off the head or whatever? So there are sort of well-known ways to do that. And we can put that axiomatization into our program, and then we sort of rely on the backing verifier to use it. So we do have benchmarks that do that, yeah.
I noticed that you are using the concrete trace. So what's the performance? I mean, every time you search the candidate program.
Yeah. So we have to be a little bit careful about how we do the execution so that we don't have loops that run for a long time and things like this. So we have to be smart about how we generate test cases. For our benchmarks, none of the programs were very large, so we're able to collect those execution traces fairly quickly. But as you get larger and larger programs, it could be the case that becomes a performance bottleneck to collect those execution traces.
Yeah. The abstract semantics of the program.
So you can take it offline?
Yeah. Okay. So.
Just a very simple question. Can you just align two programs with the side effects, for example, memory operations?
So we ultimately rely on the backing single program verifiers to do the actual verification. So if those backing verifiers can reason about side effects, then we'll run execution traces and come up with what we think is a good alignment and hand it off to the verifier. So, but one of the advantages of this approach is that we get to leverage whatever the backing verifier can do. So if the backing verifier can handle effects, then we can produce alignments that maybe will work. Yeah.
Okay.
Yeah. Thanks.
Yes, so oftentimes loop alignments are not 1-to-1, it's maybe 1-to-2, or maybe 1-to-n, where the n depends on some condition on the variables. Mm-hmm. How much of this can you support?
So are you talking about like 1 to n programs or like?
No. So like you have like a slow and a fast algorithm, and then you need to align multiple.
Yeah. So in our example, we took like we had loops that were running at different rates, right? And we can one of the transformations that we look at is duplicating loop bodies to sort of put things into alignment that way. So yeah, we have. I didn't. You should see the paper for the rewrite rules that we have, but some of the things that we look at are doing those kinds of transformations to make things sort of line up.
Okay.
Yes. Yeah.
Okay, thank you. Let's thank the speaker again.
Thanks.
And